everyone. I'm Sarah Pauley. I teach math here at Western, and pi is my favorite number, and so tomorrow is my favorite day. Why? Oh, okay, we'll talk about that more later. I need you to do something for me. So find a partner, and what I want you to do is to measure the circumference of your head. Do you guys know what circumference is? Okay, what is circumference?
Distance around.
It's this. So, yeah, it's this. So circumference, I want you to measure all the way around your head, and then I want you to measure the diameter of your head, which is the distance across. Okay? It's up to you. I need you to be consistent, though. Whatever you measure your circumference in, I want you to measure your diameter in. Once you get those, please come up here and tell me your results. Okay.
We're only measuring one person's. Are we doing both?
No, both.
Oh, both people.
Both. We need more data points. Yeah, so this is going to be a little bit. Oh. Hold on. My Excel sheet isn't working. There we go. Yes.
Across from ear to ear or from front to back?
What do you think?
Well, I don't have a round head.
Do the best you can. Yes, and I had some from, Steve has some, and I forgot to get them from him. Okay, are you ready? Mm-hmm. What do you got for your 55 and 15, and then 56 and 16. Okay, 59, 14,
58, 14.
Oh, 58, 14. Okay, when you're done, come and give me your circumference and diameter measurements. What do you got, Cindy?
Mine is 54
Ooh.
and 15.
Okay. What is Chuck's? 57 and 19. Okay, Josh. 57.5 and 16.5. Okay. 59 and 18. Okay. Hannah.
57 and 17.
17.
7 and 18.
Oh, you guys have like the same head. All right, what do we got? I need diameter also.
Oh.
So you got circumference. Go get diameter for me, Marco. What do you got? Okay, 52 and 29. And then you had 60 and 31. Great, thank you. Did you get yours?
I did, and I forgot.
Can you do it again for me? Thanks. I need circumference and diameter. Oh, Excel, don't do this. Excel is not responding.
Technology in general with you,
I don't know. I haven't done anything that is. Hold on. I'm going to have to write it down because my Excel. So what did you get?
56.
56 and 15?
Yep.
Okay, great. Thank you. Oh, Excel, come on. Don't do this to me.
It might just need restarted.
I know, but I have all the numbers.
That was a joke.
Oh, like my. Oh, come on. Okay, what do you got for me, Brian?
55.
Okay.
55 and a half. And 57.
So let's
That's
see.
all.
55 goes with 12.5.
55
Okay.
and a half goes with 12.5.
Okay.
57 goes with 19.
Thank you. Perfect. All right, let's see if Excel will do this for me. I have a feeling it's not going to. Anyone else? You have them written down? Thank you, Chuck. Hey, you guys, what units did you use?
Centimeters.
Centimeters. Anyone else use something different? 17.5.
That was on our.
Was that it on the tape measure? Okay, Marco. 18, hold on, 52, 29, 60, 31. Okay, what do you got for me? 55 and 17, 56 and 17, 58 and 19. Thank you.
You're welcome.
Okay, so let me see if Excel is going to let me do this. But I have, how much do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 people, right, that have done their circumference and diameter. So let me enter these really quick. Now, what are some of the things that you think maybe we might have some error in when measuring these?
shape.
Yeah, what do you mean shape?
It's not perfect circle.
Yes.
It's hard to measure that.
Right. So when you get that circumference, it's probably not a perfect circle. What else?
The amount of hair you have.
Yeah. Or don't. What else is the problem with finding these measurements?
Human error.
Human error for sure. Did you guys have any issues finding diameter? Yeah, so diameter is tough. Yeah. So how do we do that, right? How do we find the diameter? Dr. Goff was asking me, like, do you want to go diagonal? Do you want me to go like this? How do you want? I'm like, I don't know. I just want you to find the diameter. So we could have some issues, right, with the being perfect here, and that's okay, because what in life is perfect other than mathematics? And so let's do, I'm going to do a ratio here. What is a ratio?
Comparison of two different numbers.
Yeah, so comparing two different numbers, right? And in mathematics, we can use ratios for a lot of things, and we really do division when we talk about ratios in mathematics, right? So just for the fun of it, because what else are you going to do? Because you don't have class right now. Let's just divide these two numbers. Want to? You do? Great. Let's do it. Okay, so I'm going to take the circumference of this first person, and I'm going to just divide it by its diameter. Well, that's interesting. I get about 3 2/3. Yeah? So that just must be that one person, right? Has a ratio between the circumference of their head and the diameter of their head is about 3, closer to 4. But let's just see what other people have. Ooh, interesting. Oh, come on. Oh, something's wrong on some of these. But let's look at this. We have some strange heads in here. All right. So what do you notice about these numbers, about this ratio between the circumference of your head and the diameter of your head?
Somewhere between 3 and 4.
Yeah, they are more similar than maybe you would have thought would actually happen. Isn't that weird? Isn't that kind of cool? So look at this. So we have about 3 2/3, then we have about a 3 1/2, and we got some 4s. Those are the smarter people, right? Because they have the bigger brains. Then 3.63, ooh, 3.4, 3.27, 3.35. I really like that 3.1666 repeating. That's great. 1.79, I'm wondering if there's some measurement error there, but that's all right. 1.9, 3.2, 3.2, 3.04, and we got 3. Why did I kind of really like that 3.16? Because it's closest to the number pi. What is the number pi? About 3.14. So we talked about tomorrow's like my favorite day of the year. I don't really care about my anniversary or my kids' birthdays. It's tomorrow. Yes. So tomorrow is Pi Day, and let's talk a little bit about pi. So I had you measure your head. We measured the circumference, we measured the diameter, and we found that we all got around 3. And the reason for that is because there is a ratio between the circumference of a circle and the diameter of a circle that really makes it be a circle, right? And that ratio, when you take the circumference and you divide it by its diameter, what is the number we get? We get this number called pi. Do you guys get the cartoon? There's a pirate sitting in class, and it says area equals pi what squared? Long John, you should be able to answer this. R, yes? Pi r squared is your area. So, yeah. So what is pi? If you look at this, it's going to be the circumference divided by the diameter, and it's about 3.14. So this is a really good visualization of here's the diameter, and they take the diameter, here's 1 diameter, 2 diameter, 3 diameters, and a little bit more of that diameter is going to give us the circumference of that circle. Here's another visualization of pi. It'll get going here in a second. There's 1 diameter, 2 diameters, up to 4 diameters, and then we take that wheel, and do you see how that wheel stops? At about 3.14 of the circumference, right? Or excuse me, 3.14 of the diameters, okay? So that's what pi is. The myth, the legend, pi. It's about 3.14159, and then you can keep going, 26535, and you can keep going to the numbers of pi. How long can you go? Yeah, even longer, right? Yeah, so you can keep going forever because pi is what we call in mathematics an irrational number. What is an irrational number in mathematics? What do we consider an irrational number? You've probably heard this before. Brian. No? So irrational numbers in mathematics are numbers that cannot be written as a fraction, right? Something, a decimal basically that ends. Like 1/2 isn't irrational because we can write it as 0.5. 1/3 isn't irrational. Now its decimal doesn't end, but what happens with 1/3 as a decimal? It repeats. So as long as a decimal ends, or as long as you have a decimal representation that goes on forever and repeats, that's what we call a rational number in mathematics. Irrational numbers are numbers that never repeat in their decimal form, and they never end, okay? So an irrational, anyone know of other irrational numbers in mathematics? Square root of 2 is irrational? Good job, Chuck. You've been studying. I'm proud of you. What else? What's another super famous irrational number that we use a lot in? E. Yes, E. E is a really famous irrational number too in mathematics. So it's infinite, it never ends. And then if you've seen this talk before, you've seen that this is pretty cool. If you have your phone, so because pi never ends, it goes on forever, we can get any combination of numbers that we want to find in pi. So this is crazy. It goes on forever, it never ends, and it never repeats. So that means any kind of number combination that you want to find, we should be able to find that in pi. So if you have your phone, go ahead and scan this QR code, and you can find where your birthday is in the number pi. I always forget where mine is. Let me look. Piday.org is a great website too that has a lot of fun stuff. So put in your birthday. Now, I think Lucy is it yours that isn't in there? No, it's not saying that it's not in there. What is it saying? That it's not within the first million digits of pi. So this program only calculates in the first million digits of pi. My birthday is at position 9,230. What'd you get? 10,030? Who else? 84? Whoa! 84! 29,000, is that what you said, Katrina? Now, this is only the first million digits because we can't do all of them, right? I believe right now pi has been calculated out to 1 trillion, I think is what I saw. But we don't need it to 1 trillion decimal places, right? That's just for fun, because it is fun. Okay, chemist. Did you guys find it? Okay, and this little cartoon just has pi. They're at the bar having a beer, and of course it's 2 chickens at the bar. And he says, whatever you don't talk to that guy, he'll go on forever. Ha ha ha. All right, some history of pi. First, this little cartoon says the brain is saying to the heart, it's not pi, it's pi day, not pi day. And the heart says, I don't understand what you're trying to say. And the tongue says, stay out of this brain or I will destroy you. Okay, so some history of pi. Pi's been known for about, it's probably been known even for longer than this, but we can look back to the Babylonians and the Egyptians actually talked about an approximation of pi almost 4,000 years ago, like 2000 BC. They knew that the ratio of a circle to its diameter is about 3. And if you read at all about like the history of mathematics, it's interesting to think about how people knew, like, okay, if I make a circle bigger, that means that I'm going to have the length across that circle must get bigger as well. And that sounds really trivial to us, right? Because we're like, well, yeah, obviously. But if you're thinking about that as you're trying to understand like your world and using mathematics to describe it, that idea of a ratio is a big deal. Like if I increase the perimeter of this rectangle, that means that the area encloses also gets bigger. It's this whole idea of a ratio between some stuff with geometry. It doesn't always have to be geometry, but known for about 4,000 years ago, the Babylonians calculated the area of a circle by taking 3 times the square of its radius, and the area of a circle is pi r squared. So that's pretty close. 3 is pretty close to pi. And they estimated it to be about 3.125. The Egyptians calculated it in 1650 BC to be about 3.1605. That's pretty good. Within 200ths of it. And then the Jewish Talmud, I'm sure I said that wrong, in 500 AD said that which in circumference is 3 hands broad is 1 hand broad. So when they say 3 hands broad, they're talking about the circumference, and then the diameter would be like a third of that, kind of. I'm going to say this wrong. There is Hindu knowledge summarized in a text of theirs. I'm not going to say it. So if you have your calculator and some scratch paper, let's do what this text said. So this text said, add 4 to, this was in 499 AD, okay? Add 4 to 100, okay? Then multiply that by 8. So 4 to 100. Okay, then multiply by 8. You got to remember this was in 499 AD, people, so give them a break, right? So times 8, and then add 6,000 to 62,000, okay? Then they say the result of this is the circumference of a circle. So what was this? What did you guys get? Say it louder, Lucy. 832. They're saying that the circumference is 62,832 of a circle whose diameter is 20,000. What did we say pi was? It's the circumference divided by the diameter, right? So will you take that 62,832 and divide it by 20,000 for me?
I got 3.1416.
That is pretty good, right? So for about 500 AD, which was what, 1,500 years ago, about, they had a way that they calculated that diameter given that they knew that this was the circumference. And that made pi about 3.1416, which is 3.14159. That was really good, a long, long time ago. History pi, how did we determine pi? How did they determine the circumference of a circle? What is going to be the issue with finding the circumference of a circle? The size of it could be, especially if you're trying to actually like measure it, like actually do it, right? With the Egyptians, I was reading a history of pi book. I'm sure you all have read it, right? A history of pi book. Oh, whoa! And the Egyptians, what they would do is they'd take a stake and they would take a piece of string and like make a circle in the sand, right? And then they could take another piece of string or rope and go through where that stake was and get that diameter. And then they would see that that diameter would fit about 3.14 times around. But they could estimate the circumference of that circle with that piece of rope, right, if they knew how long that was. But what is the problem with getting the actual circumference of a circle? Yeah, where do you start, where do you stop? Also, it's pretty easy to find the circumference of a square, or also known as perimeter. Those are straight lengths, yeah? It's going to be more difficult to find a formula for finding circumference when you have something that is round, as opposed to something that is nice and straight, and we can just take a quick measurement of that. So the Archimedes method oh, I might not be showing. This was in 287 to 212 BC, and then Zhu Shongzi also was known to use this method, and it gave us the first theoretical measurements of pi. And the whole idea on finding this was finding the circumference of a circle between two polygons. Does anyone know what a polygon is?
The multi-sided shape.
Yes. So really, it's like anything with some straight edges, right, that make a shape. So when we look at a polygon, we might, oh, guys, this is going to be bad. I'm just going to warn you. What is this? An octagon, I think I drew? So if I put a circle, oh, this is not going to be a circle. Just pretend. Oh, you guys.
It's not bad.
It's like the best circle I've ever drawn. Oh, no, that's bad. Oh. I think we need to step away from it. So what would I know if I could measure this polygon, which is going to be easier because it's straight? I would know that the circumference of this circle is going to be less than the circumference of that polygon. Does that make sense? And then I could also take another polygon, and I could put a polygon that I know is going to have a less circumference or perimeter than that circle. So now what have we done? We've squished the circumference of that circle in between the perimeter of two polygons. And then now I have an estimate, right, for that circumference. Now, how could I do even better? Yeah, more lines. So let's take that polygon, and instead of having an octagon, you have whatever you call one with 12. What is that, Chuck? Is that 12? What's a 10 one then? Listen, I'm not. Oh, good. I'm glad I was just seeing if you knew what it was. Good job. You passed. Okay. So that was the Archimedes method, and Archimedes estimated pi to be between 223 divided by 71 and 21 divided by 7. So will someone please take 223 and divide it by 71 and give me the decimal approximation for that? And let's see how close Archimedes was.
3.1408.
Oh, boo. No, just kidding. That's actually really good. What about 21 divided by, oh, I can do that one. I really can. I have a master's degree in mathematics, and that's what I got, being able to divide that. Well, I guess, Chuck, if you want me to be right about everything, then yes. I should have put, thank you, the 21/7 first. Pi is less than 22, 3 over 71. Yes, I have that switched. Thank you, Chuck. All right, what now? Shongzi, I was reading, how do I say it? Did I say that incorrectly? Shongzi? I think so. I was reading about him, and he was a very famous mathematician in China, and they actually aren't sure how he got so close, but they think he must have done it by inscribing a circle in a 24,576 gon. So you smarties that know what they are, what is that? Huh, Bill? Come on. What is that? Told me what a dodecahedron was. What is the 24,576 gon? Okay, what is that? What do you guys get if you take 355 and divide it by 113? Will someone tell me what we get?
3.141592.
That is really good. That's super close. Pi is 3.14529, I think, or 592. Yeah. What else is it? Did you get more?
Just 9292.
9292. Really, really close. And they think that he did that by inscribing 24,576 gon. You guys, he didn't have calculators. He didn't have computers. This was all by hand. Pretty amazing. Yeah, he might have had an abacus, right?
Yeah, one of those, that counts as a
Yeah,
computer,
that's true.
counts.
That's true. All right, a little bit more history of pi. Where did we get the symbol for pi? This is attributed to William Jones. He was Isaac Newton's pal. And they think that it came from the Greek word for periphery, which loosely means circumference in Greek. And the P is the letter pi, right, in the Greek symbol. Before they had like a symbol for pi, they used to say things like, well, it's the quantity which, when the diameter is multiplied by it, yields the circumference. So on your Diffie-Q test tomorrow, I'll say, please find the cosine of the quantity of which the diameter is multiplied. No, I won't do that to you, I promise. And then, of course, like the rock star Euler, right? Euler was the one who really popularized using the symbol pi. When he started using it, I think I had read it was like in 1737, when he started regularly using the pi symbol, that's when we adopted it. Okay, guys, more pi. A couple other interesting things about pi, and I'm running out of time, so we'll do this quickly. If you've had calculus 2, you know what an infinite series is, but we can actually approximate pi divided by 4 by doing the infinite series for arc tangent, okay? And that can get us really, really close, right? Depending on how close you want to be, just keep adding one of these terms of the infinite series. The record for reciting pi is to the 7th, I haven't looked at this lately, but 70,000 decimal places, and that record was in 2015. So, you know, what are you doing over spring break?
Sleep.
Work on it. No, you can memorize 70,001 places. And then, do we need 70,000 places, though? No. For actually using pi for things, we really actually don't need too many decimal places to get an error that we're comfortable with. So if you, at NASA's Jet Propulsion Lab, they only use 15 decimal places of pi. They don't use any more than that. Only 15. Only 15. And I thought this was really interesting. So if you try and get the Earth's circumference using pi, if you only use 9 decimal places, then you're only going to be off by a 1/4 inch error for every 25,000 miles. So why are we calculating pi to the trillionth decimal place?
Because we can.
Because we can, because it's fun, yes? Good, I'm glad you agree with me. All right, so tomorrow, celebrate Pi Day, be irrational, yeah? Also, come to the MAC tomorrow, students, not faculty. Come to the MAC tomorrow morning. There might be something to do with Pi Day with some prizes involved. So if you come here 8 a.m. tomorrow, or anytime tomorrow, anytime you have time, there will be some stuff on the board, and you might be able to win a prize. So come by. All right, you guys, and have a wonderful Pi Day. Thank you for coming.
Yay.